Hey guys, welcome to our lesson for section on sequences with some series followed directly after this. It's going to be a little two-part video, first part sequences, second part series. We're going to have a little fun. So first of all, what is a sequence? Well, very simply, a sequence is an ordered list of numbers. I don't want red. Okay. And in general, this list could be finite, so it could be a fixed number of things, or it could be infinite and go on forever. And the way we talk about the terms or the individual kind of items in the list, numbers in the list, is we refer to them by their order, their place in that list. And so in general, we'd say like the first term, second term. When we talk about the nth general term, we use the notation A sub n to denote this. And so this subscript tells us the term number. So a sub 1 would be the first term, a sub 2 would be the second, and a sub n is the nth term. So here in this first example, we are given the kind of a formula for the sequence. Sometimes sequences can be given by nice simple formulas like this. Sometimes they're given by formula where you have to know the previous term to be able to do it, and sometimes you need to know the previous two terms and things like that. And so what we want to do here is it wants us to write out the first four terms of the sequence. So this works very similar to function notation. So to figure out a sub 1, notice I've replaced the n with a 1. And so in the formula, I'm going to replace the n with a 1 again. Okay. And so a sub 2, 3 times 2 plus 12. Right, and we just keep going. And we can see here very simply that this is a linear function. 3n plus 12 goes up by 3 every time. A sub 3 is going to be 21. And a sub 4 is going to be 24. Okay, pretty nice, right? Now this next one here, B, again, we're going to do the exact same process. So a sub 1, we replace the n, the 1, and negative 3 to the first power is just negative 3. A sub 2 is negative 3 squared. Now it's really important to notice the parentheses on here, right? And you're going to see that on your calculator. If we don't have those parentheses, we type negative 3 squared, it's going to tell us negative 9. Because your calculator reads that as negative 1 times 3 squared. But by putting these parentheses, we get negative 3 times negative 3, which gives us positive 9. A sub 3, right? Negative 3 cubed is negative 27. And finally, a sub 4, negative 3 to the fourth, gives us positive 81. Now, this next one here is a little weirder, and this is one that's going to require a little more work. These first two were pretty simple functions, right? We had a linear function and kind of an exponential function with a negative base, so it wasn't exactly an exponential function, but it works for this example because n is the order number, so it has to be an integer. Not just an integer, but a positive integer. So n in all of these sequences will always be a positive integer value, right? Because it's the number, it's the position in this list. So it's either going to be 1, 2, 3, 4, 50. You're not going to have the 3.5th number, right? You're not going to have a negative 7th number. And so it's always a positive integer. Makes it really nice. Now, down here, right, we kind of have an idea of the setup here, but we don't really know necessarily just looking at this what's going to happen. Right? I'm not able to look at this like I was the example in part B or in part A and be like, oh, part A, we're growing by 3 every time. So we went 15, then 18, 21, then 24. Part B, we're just multiplying by negative 3 kind of thing each time. So negative 3 times negative 3 is 9, times negative 3 is negative 27, times negative 3 is 81. Right? We don't have that nice, clear, exact thing going on here. So we kind of want to piece this together and be kind of careful. So 3 to the first is just 3. Now I have -1 to the 1 plus 1. So 1 plus 1 is 2. So -1 squared is 1. We get 1 plus 6. So this is 3/7. A2 is going to be 3 squared over -1 to the 2 plus 1 plus 6. So 3 squared is 9. Now 2 plus 1 is 3, and -1 to the third power is -1 plus 6. So this is actually 9/5. Okay. Go down. We have a sub 3. It's going to be 3 cubed. -1 to the 3 plus 1 plus 6. 3 cubed is 27. We know we're going to have our 6 over there. So now we look at this. So we have 3 plus 1 in the exponent. It's 4. -1 to the fourth is 1. And so we end up with 27/7. And our last one, a sub 4, 3 to the fourth, -1 to the 4 plus 1 plus 6, 81. 4 plus 1 is 5. -1 to the fifth is -1. We get 81/5. So the way we write these lists, so we've gone through, we found the first 4 terms of the sequence. But I want to write these down kind of in the formal way we would write down a sequence. And that is very simply by listing them separated by parentheses. So this first one, example A, would be sequence be 15, 18, 21, 24. Our next one for B would be -3, 9, -27, 81. And our last one C here would be 3/7, 9/5, 27/7, and 81/5. And if you're looking at that and seeing a pattern there, it's absolutely correct. The denominator is alternating 5 and 7, 5 and 7, or 7 and 5, 7 and 5, whichever way. And the numerator is just powers of 3. And so that just increases 1 each time. So the next term here would be 3 to the 5th over 7. And so we can kind of see how that goes. It kind of makes it nice and easy for us to kind of figure out. So this is what I was talking about. So this is what's called a recursive formula. This formula relies on us to know the previous term to know the next term. These occur every now and then, but they're not something we use a whole lot. So I'm going to go through this example. We'll probably kind of leave these as it is. So we want to find the first 4 terms again. We know a sub 1 is 9. We're told that right here. So now a sub 2 is -4 times a sub 2 minus 1. So that's -4. So 2 minus 1 is 1. So this is -4 times a 1. Which is -4 times 9. Which gives us a lovely -36. So a sub 3 is going to be -4 times the previous term. So -4 times -36, which can give us a positive 144. And a sub 4 is -4 times the previous term, which can give us a -576. So our sequence is 9, -36, positive 144, -576, and so forth. Okay. So these dots, these ellipses, if you want to use the technical term, ... just means continues the pattern, right? So we're saying that this sequence will continue on, continuing the pattern until it stops, whenever that may be. Okay. Now this is a very famous sequence, the Fibonacci sequence. It is defined by a double recursive formula. So what I mean by a double recursive is you need to know not just the previous term, but the previous 2 terms. Okay. And so the Fibonacci sequence starts with A1, equaling 1 and A2 equaling 2. And then we can define every other term in this very simply by A sub n is equal to A sub n minus 1 plus A sub n minus 2. So all we're doing is we're adding together the previous two terms of the sequence. And I just made a mistake here. The A sub 2 is 1. Sorry. So then A sub 3 is just the sum of the previous two. So 1 plus 1 gives me 2. A sub 4 is 1 plus 2 gives me 3. A sub 5 is 2 and 3. It's 5. A sub 6 is 3 and 5 gives me 8. Lastly, A sub 7 is 5 plus 8 gives me 13. And so the first 7 terms of a Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, and then the pattern continues as is. So, very cool. Now, any ordered list of numbers is a sequence, but there's special sequences that we want to talk about that have special characteristics and traits that make them easier to deal with and for us to be able to work with them. And the first of those is what's called an arithmetic sequence. So an arithmetic sequence has a first term A1 and it has a common difference D. So this is what makes arithmetic sequences very important, is they have a common difference between any two terms. So it doesn't matter what term you take, okay? So D is equal to A sub n minus A sub n minus 1. So you pick any two consecutive terms and find their difference, and that is our common difference D. No matter where you're at in this sequence, that is the really cool thing about this arithmetic sequence. So if we look here, so told find the nth general term for this sequence, and then find A19. So the first thing we need to do is figure out, is this actually an arithmetic sequence? Because if it's not an arithmetic sequence, we might not be able to find this. We might be able to identify a pattern, but we don't really know. And so what we need to do is we need to look at the difference between each set of terms. And so when you're given a sequence like this and you're trying to figure out, is this arithmetic, it's not enough just to find the difference between the first two terms and say, that's my common difference, I'm done. We have to make sure that it works for every set that is given to us in this problem. And so if you look, the difference between each term is 0.5, or in this case, actually negative 0.5. Negative 0.5, negative 0.5, negative 0.5 for all of them. Especially the other ones. Same. So that tells me that D is equal to negative 0.5. Okay. I think I have this backwards up here. And minus 1. There you go. Fixed it. D is equal to A sub n minus 1. No, I was right. I'm going to go back and undo my unmistake. So we take A sub n, so in this case, say A sub 2 is 8.5, subtract the previous term 9, and we get negative 0.5. Yes, I was right. Good. So what I know is every single time this goes up, we can use this difference to figure it out. Now, what's really cool is we know functions that have a common fixed difference, and it's a linear function. And so we can actually find a general term, a formula for the general term of an arithmetic sequence. And it comes down A sub n. So the general term, A sub n, is equal to the first term plus n minus 1 times D. So D is this common difference. Now the n minus 1 is kind of a why would we do that part? Why wouldn't it just be n? And the reason why is because this sequence starts at 1. And so if we did just n, then that means A sub 1 would be A1 plus D. And that's not what we want because we're using A sub 1 here. Okay, if we had an A sub 0, then we could just say n, but because we don't, we have to start with n minus 1. So given this information, for example, 4, we know what our a sub 1 is, and we know what our d is. So I can say that the general term a sub n is equal to 9 plus n minus 1 times 0.5. And so we have this nice general form. We could simplify this absolutely, right? We could multiply by 0.5 and combine like terms, but it's not necessary. And for the purposes of this class with me, it's not necessary to do unless I specifically say to simplify the equation. You don't need to worry about it. So it wants us to find a sub 19. 9 plus 19 minus 1 times 0.5, right? So we're just replacing, instead of a sub n, a sub 19. So it just works like function notation. I replace the n's within the equation with whatever I have down as my subscript. And so this is 9 plus 18 times 0.5. And 18 times 0.5 is 9. This is 18. Aha! Big mistake I made on this problem. And hopefully you guys have already saw it and been like screaming at the screen, but Mr. Keeling, you're doing this wrong, and that's perfect. Right? We're all human, we all make mistakes. And D is not 0.5, D is negative 0.5. Negative 0.5. 9 plus. So our A sub 19 is 0. All right, cool. Let's look at this one. Another example. So here, a person's salary is $60,000 in the first year, and it will increase by 5% each year. So write out the first few years of the salary and then find the nth general term. So this is pretty easy, right? We see it's increasing by a percentage each year, so the antennas in our head should go, ooh, this is an exponential. Okay. So in the first year, a sub 1, he makes $60,000. In a sub 2, he makes 60,000 times 0.0 times not 0.05, 1.05. And in a sub 3, he makes 60,000 times 1.05 squared. Okay, let's do one more. If a sub 4, 60,000 times 1.05 cubed. And I could, put a little 1 here, and I could even 1.05 to the 0. Then you may be like, why would I put to the 1, and why would I multiply this by 1.05 to the 0? That's just 1. But it helps us kind of see a pattern here. And notice, right, this is similar to the the arithmetic sequence where we had this n minus 1 component. Notice the exponent here, right? If we think of this as an exponential function, our input would be that exponent. Notice our kind of input and our exponent are one off. 1, 0, 2 and 1, 3 and 2, 4 and 3. So our formula here is going to be a sub n minus 60,000 times our 1.05, the n minus 1. Now let's turn that into an official statement. So we had arithmetic sequences, but we also have another type of sequences that are very important. As you can see from this last example, it is something to deal with exponentials. And so if the ratio of any term in a sequence to the preceding term is a constant r for every such pair of terms, then the sequence is a geometric sequence. And we call R the common ratio. So let's unpack this, the any term ratio of it and its preceding term. So what that's simply saying is if we take any term, a sub n, and take the ratio of that term to its previous term, okay, if this equals a fixed constant value r, then that is a geometric sequence and the common ratio is that r value. What's really cool is it's a very simple equation. A sub n is equal to a sub 1 times r to the n minus 1. And so we have a very nice, clean, simple formula for both arithmetic and geometric sequences. And so really the trick comes down to figuring out which type of sequence we're dealing with. And from there, then just finding either D or R and going from there. So here, our example, we want to find a formula for the nth general term given this information about the sequence. So we have to figure out, is this arithmetic, is this geometric, or is this neither? If it's neither, we can't give a general formula for it necessarily. We don't have the ability to do that. I'm not worrying about doing that. But if it is arithmetic or if it is geometric, we need to find either the common difference or the common ratio and set up our equation. So this first one here, notice from 7 to 7.1 adds 0.1, adds 0.1, adds 0.1. So this is arithmetic, which means my general term is going to be a sub 1 plus n minus 1 times d. Well, what's our first term? 7. What's the common difference? What happens when I go from one term to the next? I add 0.1, so it's a positive 0.1. And if you want to use 0.1, it's fine as well. And there we have it. That's it. That's all this problem is asking us to do. Okay. So I look at my next one and I see, okay, from the first to the second, I subtract 2, subtract 1. That's not arithmetic. Those aren't the same. So that's definitely not it. But maybe it's geometric. And so I need to take a term divided by its previous. Okay. 2 divided by 4, that's 1/2. 1 divided by 2, that's 1/2. 1/2 divided by 1, that's 1/2. If we continue to check, 1/4 divided by 1/2 is 1/2. 1/8 divided by 1/4 is 1/2. So this is geometric. And r is equal to 1/2. So since it's geometric, a sub n is equal to a1 times r to the n minus 1. So our first term here, our a1, is 4. Our r value is 1/2 raised to the n minus 1. So these are really simple this way. Like it's really this easy to do. It's really nothing too complicated or crazy. We want to try and keep these as simple as we can. Don't overcomplicate things in your head if you can help it. But what about here? Here I'm told we're dealing with a geometric sequence. But I'm not given either the first term or r. I'm given these other two terms. What we could do is very, very similar to what we did with an exponential function. Remember, we have these tools to deal with exponential functions, and we have this general formula. So since I'm told that it's geometric, I know my general term is going to be a sub n times a1 equals a1 times r to the n minus 1. So that means a sub 2 is going to be a1 times r to the 2 minus 1. And this equals 1 because a2 is 1. And a8 is a1 times r to the 8 minus 1. That's going to be 64. So let's clean up these two equations real quick. Okay. So to clean them up, I get the first equation is 1 equals a1 times r to the first, because 2 minus 1 is 1. My second equation, I get 64 equals A1 times R to the 7th. All right. Now, if you remember, this is a very, very similar problem, right? If you will, if you imagine, I said find the exponential function that goes through the point 1, 1 and 7, 64. We would solve this in the exact same way. We want to find the equation with the lower exponent, which in this case is our first equation. And we want to divide the other equation by that. So what we get is 64 over 1 equals A1R to the 7th over A1R. So our A1s cancel. This R goes away. This 7 becomes a 6. And 64 over 1 is 64. So what we end up with is the equation 64 equals R to the 6th. Now, square root, or not square root, sixth root both sides. We get R equals 2. Now, what we have to do, we're not done. Now, first of all, could this be a negative 2? Right? And we really kind of don't know. It's possible that it could be a negative 2. What we have to look at is we have to look at the terms that were given. And really, we just kind of have to make a kind of a guess sometimes. For the most part, it's going to be very obvious if something like that is going to happen. But I'm not going to do that kind of trickily. So, just as we did with exponential functions, we look at one of our two equations. Okay. And we plug in this R value into either one, whichever one's easiest. If I look at this left one, I have 1 equals A1R. That's really easy to deal with. So I get 1 equals A1 instead of R, we know R is 2. Well, just divide by 2. And we get that A1 is 1/2. So now, we know that R equals 2. And A1 equals 1/2. So I can say that my general term, A sub n, is A1 times R to the n minus 1. And that's it, guys. This is how easy it is. Now, I want to do one more example, okay? I want to imagine we have an arithmetic sequence. I know this one isn't written on here, so make some room. We have an arithmetic sequence. And let's see here. I'm going to make this up on the spot. So we'll say that A sub 3 equals 31. And we'll say that A sub 8 equals 56. All right. Okay. So again, we're told arithmetic. So we know A sub n, A1 plus n minus 1 times d. So we set up two equations. We know A3 is going to be A1 times 3 minus 1 times d. We know this is going to equal 31. And we know that A sub 8, which is A1 plus 8 minus 1 times d, is going to equal 56. So if we clean those two things up a little bit, we get get 31 equals, this is supposed to be plus, equals A1 plus 2d. And then over here, we get 56 A1 plus 70. So you guys know how to solve this because you guys have done matrices, right? This is a system of equations. You could solve this absolutely using systems of equations. A1 would be X, D would be Y. You solve it that way. We can also just solve it by hand, either substitution or anything like that. But if we think about this, this is kind of like slope, right? D is kind of like the slope of a linear function. So D is equal to essentially the slope. So the output of our second point is 56. The output of our first point is 31. The output of the input of our second point is 8. And the input of our first point is 3. So 56 minus 31 is 25. And 8 minus 3 is 5. So D is 5. So now we just 31 equals A plus 2 times 5. 1 equals A plus 10. Subtract 10. A equals 21. A1. So A1's 21. And D is 5. So we get that A sub n equals 21 plus n minus 1 times 5. So there's a nice example of how to do it with arithmetic sequences as well as with geometric sequences. So hopefully you guys are comfortable with these sequences. Next up, we will be talking about series. So I will see you for part 2 of this sequences and series lesson, and we'll talk about what a series is.